Hello, calculus students. Areas of surfaces of revolution. So this is going to be when we take some sort of curve and rotate that around an axis of revolution, and it's going to trace out a surface. For example, let's say we have a curve presented as a function of x. There's some sort of axis of revolution involved that we spin that curve around. It's going to wind up producing a surface. Now, mind you, we're not revolving an area to create a solid. I'm revolving only the arc to create a surface. This is like the skin of a solid. And we want to determine what the surface area is of that solid. And it does not count the circular caps. We're going to do something very similar to what we did with arc length. We're going to try to cut this up into a whole bunch of little pieces. Let's focus on just one such piece. We're going to figure out how far that piece is from the axis of revolution. We'll call that r. And then when you spin that piece around, you're going to get this little thin ribbon. If you were to unroll the ribbon, it would produce a very long, skinny rectangle. And our goal, of course, is to determine the area of this skinny rectangle. And we got to know its dimension so we can figure out the area of the ribbon. Well, the diagonal length is the differential ds. So back when we did arc length, if you recall, we had dx, dy, and we had this diagonal ds. The ds is really how wide this ribbon is. And then the other dimension is going to be the circumference of this circle. And since the radius of the circular ribbon is r, then the circumference is going to be 2 pi times r. So then the total surface area would be putting all these little circular ribbons together to get the surface area of the entire surface. Let's go with SA for surface area. It's going to be an integral of all of the areas of the ribbons. So that's going to be 2 pi r times ds. And then we're going to integrate from x equals a to x equals b. And this is your basic setup. Now the ds in this is the same as the ds we did in arc length. It's going to be 2 pi times r, and then the square root of 1 plus dy dx squared, and then dx. And the other catch is that this r here, notice it's not consistent. If I were to imagine a strip up here, it would have a longer r. A strip down here would have a shorter r. R is also going to be a potentially changing function of x. Now, if you're doing a curve presented as a function of y, you revolve around an axis. The axis I drew over here was horizontal, but I could have done an image of a vertical one and called this r instead. So it doesn't really matter which way the axes of revolution are, whether they're horizontal or vertical. I'm just going to draw both of them horizontal. So if we revolve around this, we're still going to take a little strip here. It's going to figure out how far away it is from the axis of revolution. We're going to call that r still. And the only difference in our formula is going to be that the surface area will be an integral from y equals a to y equals b. So we'll do everything in terms of y this time. And it'll be 2 pi r, and then the ds. And the ds in terms of y was 1 plus dx dy squared, and then dy. And then the r in this needs to be a function of y. And that's true if the axis of revolution is horizontal or even if it was vertical. It doesn't matter. Whatever the axis of revolution is, you need to somehow express the radius as a function of y. Okay, let's move on to the first example. A surface is generated by revolving the curve below around the indicated axis of revolution. Find the area of the surface. So y equals x squared, looks roughly like this. And we have a parabolic arch. So the x-axis, which is the equation y equals 0, is our axis of revolution. Draw a little snippet of this and see if you can figure out what the radius is going to be as a function of x. Well, the length from the x-axis to the curve is given by the y-coordinate. So you could just say y, but we want to do this in terms of x, so we're going to say x squared instead. And that's really the hardest part of doing this, is determining what that r is. And so our setup is going to be the surface area is equal to an integral, x equals 1 to x equals 3, 2 pi r, and the radius is just x squared in terms of x. The ds will be 1 plus, and then we put the derivative of y with respect to x is just 2x, and that's what goes inside these parentheses, and that needs to be squared, and then you finish off with the dx. I'm not going to actually do these integrals by hand, but you're welcome to do it. I see a sum of squares in here, and the function being squared, you want to set equal to the square root of that number, which is 1, and then times the tangent of a new variable u. So this would be the trig substitution that would help get us out of this particular integral. But if you went straight to a calculator to get an answer, and you would get a total of 257.5 approximately square units. Now keep in mind we're finding an area. Okay, we're going to do the same example, but revolve around a different line, just to see how the r changes. Once again, draw an image. Have the x-axis through here, but that's no longer the axis of revolution. We're going lower to y equals -2. Imagine a little snippet here. the r is going to be from function all the way down to that line down there. Well, this part of it is given by the y-coordinate of the function, which is x squared, and then this length here is 2. So the r is going to be the sum of those two lengths. You can also think of it as doing the top curve minus the bottom curve. So you would do the function x squared minus negative 2. That winds up giving the same result. And everything else about this problem is going to be the same. So our total surface area is still going to be an integral from x equals 1 to x equals 3. It's going to be 2 pi times the radius of revolution, which is going to be x squared plus an extra 2. And then times the ds, which is 1 plus, put the derivative of the function, which is 2x in there, square that, and then end with the dx outside. And once again, if you're doing this by hand, you would still want to let the 2x function be equal to 1 times the tangent of a new variable. And there's going to be some work ahead of you, which I won't repeat since we've done examples like that in the past. Do you expect the answer to be more or less than it was in this case? Right, we're revolving around an axis that's further away, so that should make a much bigger surface. And sure enough, when we integrate this, we get 361.41 approximately, and square units. Compare that to the last answer, which was smaller. Okay, let's do another one. This time we're revolving around an axis that's above. So we're going to have our curve. What's that y-coordinate right there? Just curious. If you plugged in 3 into this function right here, you would get 9. So y equals 10 is clearly above this entire curve. And this is what we're revolving around this time. Imagine a little snippet of this curve and figure out how far away from the axis of revolution that is. Well, I know that this length from strip down to x-axis is x squared, and I know that this total length is 10, so we can deduce that r is going to have to be 10 minus x squared. Or you can do upper, which is 10, minus lower, which is x squared. And then from here, the setup is all pretty similar. The surface area is going to be an integral from x equals 1 to x equals 3, 2 pi times the radius, which is now 10 minus x squared, and then times the ds, which is, in this case, 1 plus the derivative of the function, which is 2x, and then square that, and then put the dx outside here. Again, you would do a tangent substitution to do this by hand, but using an integral calculator, we get 261.995 approximately square units. Now let's do the same curve presented as a function of x, but revolve it around a vertical line. And x equals 4 is clearly over here. Okay, we still draw a little snippet, and we figure how far that snippet is from the axis revolution. That is going to be our r. And we definitely know that from y-axis to the axis of revolution is 4 units long right there. How do I label how long, where that point on the curve is from the y-axis? Well, that's given by the x-coordinate. So you might say, okay, well now I have to solve this for x and say, oh, that's equal to the square root of y, and use that in my calculations. However, because our curve was given to us as a function of x, we could do this whole integral in terms of x still. This was different than when we did volumes of revolution, where how we sliced through the region dictated whether everything had to be in terms of x or everything had to be in terms of y. But here, we're slicing it by x. So all the little snippets of this curve are broken up by a partition of the x-coordinates. So everything's going to be in terms of x, meaning that the r is equal to the greater distance 4 minus the lesser distance x. In other words, you can think right minus left. The right x-coordinate is 4 and the left x-coordinate is the x. That's changing from 1 to 3. So 4 minus x will be the correct r. And our integral will look very similar to the others. We can do everything in terms of x still, even though the axis of revolution is now vertical. 2 pi times the radius. The radius is given by 4 minus x. Don't write that as square root of y because we want everything to be in terms of x. Square root of 1 plus, and then we put the derivative of the function and square that, and then we have the dx outside of the radical. And then when you reach for a calculator, and you get approximately 95.81 square units this time. All right, so that's the nice thing about surface areas, is when the information, the curve is presented as a function of x, we do everything in terms of x, regardless of whether the axis revolution was vertical or horizontal. And when you're revolving around a horizontal line, then your r's are all vertical lengths. That involves the y-coordinate, like 10 minus y, but then you change the y to x squared so that in the end, everything is in terms of x. But when you're doing a vertical axis revolution, your r is a horizontal length, which means you just need to adjust x itself. Okay, so let's go on to a brand new curve. This time we're doing a curve that's presented as x is a function of y. X equals 2 plus cosine y. Here's our curve, and we're cropping it from y equals 1 to y equals 3. So it's really just this portion of the curve that we're looking at. Remember, when I write x here, this is the x-axis. In equation form is y equals 0. We are going to integrate from one y-coordinate to the next. Imagine a little snippet here, and then how far is that from the axis revolution? If you take a point on this curve, the distance it is from the x-axis is given by the y-coordinate of that point. And since we're doing, everything was presented as a function of y, I'm going to do all my integrals in terms of y. Limits of integration will be y. We're going to use the dy version of the ds, and we want our radius to be in terms of y. And our radius, therefore, is just y. I don't need to solve this equation for y and express it in terms of x. Surface area will be an integral from y equals 1 to y equals 3, 2 pi times the radius of revolution, which is just y in this case. We are going to have to know what dx dy is now, because the formula is 1 plus dx dy, and that needs to be squared, and then dy. So I got to figure out what to put inside these parentheses. So we take a look at this expression and do the derivative of x, but with respect to y. The 2 will go away, and the derivative of cosine of y is negative sine of y. And this is one where it would be extremely difficult to do by hand. This would be just something I went instantly for a calculator and plugged it in, and we get 31.26 square units. And the last slide, same curve, but let's revolve it around a line that is vertical, and let's put that vertical line to the left. We have an x-axis in play, we have the y-axis in play, and we have an axis revolution that's over here. And then when we have a little snippet here, a little point on this curve that we're going to revolve to make a ribbon, the radius of revolution will be this length. The distance at this point is from the y-axis is given by the x-coordinate, and this length here is clearly 1. The r is going to be 1 plus x. However, since the curve was presented as a function of y, we want to do everything in terms of y. So I'm going to have to replace that x, so it's going to be 1 plus, and then 2 plus cosine y. So in other words, your radius will be 3 plus cosine of y. Once we have that radius determined, the surface area will be an integral from y equals 1 to y equals 3, 2 pi times the radius of revolution in terms of y, which is 3 plus cosine of y, and then times the ds, but the dy version of it. So the square root of 1 plus, and then again we do the derivative of this function with respect to y, which is the negative sine y. That needs to be squared, and then the dy. And we have an integral in terms of y. Reach for the calculator again on this one, and we're going to get an answer of about 43.18 square units. And there it is. We've done some examples of curves given as functions of y with horizontal and vertical axes of revolution, and in which case, because the curves were given as functions of y, just do everything in terms of y. And then the other cases where the curves were presented as functions of x, so do everything in terms of x, and we did cases that had both vertical axes of revolution and horizontal axes of revolution. And that is how you find the surface area of a surface that's been created by revolving an arc around some axis.